thermal fluid sciences experts. This is Pro-Ready Engineer.
Well, hello again. This is Bassam Abdelnabi from Pro-Ready Engineer. This is a much shorter video from the very long 2 hours video that I typically post. So if you like it, make sure to like and subscribe, and just consider watching the full video. Thank you and take care. Let's top it a notch. We are in the detailed analysis here. We're going to top it a notch. I'm giving you a system on the screen. Let's start with it. What is this system? It's a typical depiction of how pumping systems work. There's a pump sitting on the ground. That's our datum here. The word datum immediately tells you that we're going to be using potential energy, because datum, then potential energy relates to that datum. So here's a datum. There's a tube sucking, like your straw. This is your straw. Sucking the fluid, in this case, let's say it's water, from down here where the water is. And let's say this is your skyscraper that you live in, very long. And the reason we have the pump is to suck that water from there and pump it all the way up. Let's say very long skyscraper, to a tank sitting on the roof. And then this tank sitting on the roof, so water comes out, dumps in the tank, fills that tank. Then that tank feeds the whole skyscraper. Tremendous amount of water. Let's say it's a very large one, 200 gallons a minute. Something really large. This is called the suction. Your straw, where you are sucking from. When you suck with a straw, you pump in your stomach. That's not the case here. You pump to the delivery in the tank. This is called the delivery configuration. This is the suction configuration. The water level sits at H suction. This is a water level. You know what the water level means? This is 3 meters, something of this nature. The water is down 3 meters, H suction. And this is where your tank is, up top on the roof of the building. So let's say this is 50 meters, 100 meters, tremendous, whatever the number is. We call this H delivery, static delivery height, just the height. The tube length, your straw length, is L suction, and your delivery line is L delivery. When you suck, this tank is open to the atmosphere, so this water level is seeing atmospheric pressure here. The same happens to your delivery. When the water discharges, just imagine like it's literally here. If you're standing here looking at it, it will be just the water is flowing. It falls and fills that tank. It's free fall. So the pressure right here at station 3 is atmosphere, is discharging in the atmosphere. Station 3 is here. Station 2 is here, right immediate at the exit. Station 1 is right here at the inlet. And station 0 is down here. These are the different stations involved with this problem. Let's apply the energy equation that we learned today on the suction side of things. Pressure plus potential plus kinetic is equals to pressure plus potential plus kinetic plus the losses you lost along the way, losses due to friction. There is no work, there is no Q. Remember, I'm applying the equation from 0 to 1. I have nothing to do with the pump. I don't care about the pump. 0 to 1. But when you do that, this is atmosphere, it goes away. pressure here. Velocity goes away. You say, why is that? Why did the velocity go away? Maybe there was a little bit of velocity. Sure, and if it's a little bit, you can ignore it. Imagine you are pulling from the river here. Imagine you are pulling from the river. And think about that for a second. Do you think that very large water surface moves with a speed that compares to the speed in your pipe? Let me say that again. Continuity equation tells you that mass flow rate is the same. Rho AV is rho AV. In this case, it's water. Take the rho out. AV is equals to AV. So the area times velocity has to be equal to area times velocity. Let's say this is a 2-inch pipe. So that's your area. And it has a certain velocity to it. And let's say this is the tank. You see the area ratio. This area of the large tank, the river, the velocity is what? No. 1/500. Then there's no need to think of this velocity. You say it's about 0. For this example. How about if I give you another example? I always want to make sure that we are well connected. I'll give you another example where I actually give you the velocity. So well, the water surface velocity is moving at 0.5 meters per second. Okay, then use it. I've given it to you. Then use it. Right? But why don't I give it to you? Because the area ratio is largest negligible. You can take it out. So this goes out, this goes out. Why is this negative? Why didn't you just say rho GH? Right? And by the way, I say rho GH, I say GH, I say H. These are all different forms, and all what happens is you divide. Either you keep the G, you divide the full equation by the G, you keep the rho, you divide the full equation by the rho. Remember, it's one equation, you can multiply and divide, and we use this trick for some reasons. So why is this rho GZ, which is just Z in this case, is negative? Well, because I put the datum here. This is my datum. And if it's lower than the datum, it's negative. If it's upper than the datum, the potential energy is positive. Potential energy is positive if you are up top here. If it's negative, if you're down below here. Let me tell you. How about if you, when you solved this problem, you did something different? You said, no, this is my datum. I'm going to use it to solve it this way. And this point will be HD plus HS, and this will be 0, and great. You will reach exactly the same conclusion that I have here. It's not going to change. It doesn't matter. Those things, they don't matter. Whatever the way you analyze it. Good. And at station 1, I have the pressure, velocity, H lost due to friction in the suction line, right? And I plug the numbers in, and I end up with P1 equals to this formula here. The pressure of point 1 is the negative of the summation of this lift. We call this the lift, where you lifted the water from, called the lift, right? Suction lift, in this case, this is where you lift it at the suction. V squared over 2G plus the H friction due to suction. This is a formula for P1 over rho G. By the way, gamma is rho G. I want to make sure everybody is calibrated. Multiply this whole equation by G. Okay? P1 over rho, GH, V squared over 2, GH suction. Let's multiply the full equation by rho G, gamma. P, rho GH, rho V squared over 2, rho GH. Good. let's apply the same equation between station 2 right at the exit to station 3 right here. And for a second we will assume that this line is a constant diameter line, meaning the diameter of the pipe at 2 is the same as the diameter of pipe at 3. What does that mean? Well, area is the same, so the velocity is the same, right? So V2 is V3. So we can take that out. And Z2 minus Z3, this distance here, is H, delivery. Plug that in. And now you have a formula for P2 over gamma here. P2 over gamma is H delivery plus H suction, H friction on the delivery side. Now you are thinking, why did you get a formula of P1? Why did you get a formula of P2? Let's see why. Let's apply the energy equation between 1 and 2. Now the pump is involved. We're going from 1 to 2 and the pump is involved now. So it turns out this will be the equation. Where is the GZ difference? We've discussed that before. This is the same pump. These are very small differences. You take them out. There's no difference in the Z. So the work of the pump is P2 minus P1 over rho plus V2 squared minus V1 squared over 2. Now you will say, but earlier in this presentation you said work of the pump is P2 minus P1 over rho. No. When I said that V1 is equal to V2. And this is why it turned out to be like that. How about if V1, the velocity here, is not the same as V2? Well, that's the difference. And I actually even said that comment when I put it there. This energy equation is extremely simple to write. All what you need to do, write it down and put exactly what is considered and what needs to go away. But I have a formula for P2 and a formula for P1. Plug it in. From the previous slide, you end up with this formula. And this formula becomes a very interesting formula. It says take the H static suction, the lift at the suction, and the lift at the delivery, H static delivery, this elevation difference, sum them up. Plus whatever you lose in the suction and whatever you lose in the delivery, H friction delivery, and add to it the kinetic energy at station 2, and that's your pump work. And because this is a distance and this is a distance, they sum up together and they call it static head. And it's actually a very nice concept. Think about that. Think with me. Think with me for a second. Why did engineers do that? To analyze pumps. Think about that. If you go there, you are the engineer visiting this site, you are going to analyze this and build the system. You know what you will tell yourself? Here's the way you will think. You say, okay, I have the water sitting here. I want to take it there. I want to move the water from here to there. I need to lift it from here to there. That's it. That's your static head. And this is 100 meter. I need to lift it 100 meter. But I also have to pay for the friction here, that straw. I need to pay for that friction. And I need to pay for that friction. I need to pay for the friction in the suction, for the friction in the delivery. So my pump has to pay to bring the water 100 meter up, plus the friction in the lines, plus the kinetic energy in the delivery line. Let me go back again one more time, because we will kill this. Why didn't we keep this equation as P2 minus P1 over rho V2 squared and just plug it in there? Well, I think you know now why. See, this equation relates to what the pump needs to do with the system configuration that you have. Meaning, it's an immediate formula that tells you if this is what you are trying to do, bring the water from here to there, this is your, line, you measure your lines, you know how the lines will run, you know the length, you know the this, that, FLD, V squared over 2G, you know how do you calculate the friction, as we discussed. It immediately takes you there. However, the outcome is the same. But engineers, what they do is, when they have an application, like a pumping application, and that's what I'm doing here. All this detailed analysis is I'm going very detailed on how you analyze a pump system. They don't start from scratch every single time they want to analyze, let's write P2, let's write P1, let's write the energy equation now, let's substitute, let's take it now. Because by the time you are doing that, there's another engineer who said, okay, we need to lift the water 100 meters. What's the length of this pipe? It's X, and the delivery pipe, this is 150 meter. This pipe is 10 meters. It has this bend, the friction. Plug the numbers in. Here you go, and you are still applying. Oh, let's apply the energy equation. Let's put 1 and 2. We put formulas that we can put to use right away, right? But the goodness of understanding the ins and outs and the bolts and the nuts, and if there's a concept I want you to take from all my videos, that is the concept. You will be an extremely good engineer, way better than the typical engineer, if you can always go back to the first principles and arrive at the same concept. You will be an amazing engineer. So let's